All right, so we're going to kind of continue the topic we talked about last time. So we're still going to look at confidence intervals for the population mean. But today it's probably more practical for how you might actually encounter the information in a real life setting, because a lot of times you're not going to know what the standard deviation is. In other words, if there's a million values, do you remember how complicated finding standard deviation was? We had to do a whole big table or like a whole big drawn out formula. And so that's not going to be practical for a million people. Even maybe if obviously we would be using a computer for that, we just might not have the capabilities of doing it. So when we know the standard deviation, like in the last section, the confidence interval could be found by taking the sample mean plus or minus the standard error. And this is going to look more complicated than it is. Remember, this was critical value times the standard error. Okay, so remember this part just represents the margin of error we found. So don't let the letters in that confuse you. This is the thing we got from the table, the critical value, and then we figured out this as the standard of error. Sometimes we were given it, sometimes we had to figure it out. But like I said, in practice, in other words, real world settings, it is going to be much more common that we don't know that sigma. And we have a backup option for that too. We just have to find our error a little bit differently. So when we don't know the value of sigma, we instead replace it with a value that's easier to find, which is the sample standard deviation. But not surprisingly, that's not going to be as accurate because it's the sample standard deviation instead of the whole standard deviation. And remember, we call the sample standard deviation S, whereas the population standard deviation was sigma. And also when we do that, it's not going to exactly be a normal distribution. In other words, we cannot use our table 8.2 like we have been. Since it's not a normal distribution, we can't use that z-score because z-scores are only for normal distributions. But we can do a like process, and we're going to talk about what that is in just a minute. So you do need to go ahead and get out your table 8.3, that second table, the one that doesn't have two sides. And then also I would get out like a couple different colors of writing utensil because we're going to look at a graph and we're going to kind of compare some different graphs, and it's helpful if you can draw them in different colors. So because we can't use z-score, we're going to use something different that is going to kind of resemble z-score but be different in some ways. The distribution in this case is what we call the student T distribution. Okay, and if you notice, that's the title of table 8.3. Table 8.3 shows you the student T distribution. And for that, they're basically many normal like curves. I don't know why I said manly. Lord. Many So they'll be normal like, but they'll just kind of differ in height and width a little bit. So there'll be slightly different curves, and that is going to be distinguished by something that we call degrees of freedom. Sounds all patriotic, right? It's really not. In other words, the degrees of freedom is a quantity that tells you kind of which curve to look at. So if you want to know the number of the degrees of freedom, which are just going to come into play when we look at some examples, your degrees of freedom is always going to be one less than the n value that you have, okay, up to a certain point. So here's what I mean by you're going to have some curves that are normal-like. So go ahead and draw your normal bell curve. Okay, but then we might have a bell type curve that maybe has a different height and width. Okay, and then we might have another one that has a similar kind of layout but a different height. Okay, so while this one is a normal curve, this one might be a T with 10 degrees of freedom. And this one that I drew in pink might be a T value with 5 degrees of freedom. In other words, like the format's the same, it's still the most likely. So this normal distribution, by the way, is z-score. But the areas under the curve at certain spots are going to be different because we have these different heights and widths to the curve. But it's still, notice, symmetrical if you drew it right? Like my drawings kind of got squiggly at the end there, but I think you kind of get the gist of it. So let's talk about the student's T distribution. It's like an italicized T, so it's not like just a lowercase t. So the student T distribution has the following properties. It is not as accurate as a normal distribution, okay? But notice it does have some qualities, right? It is, like I said before, symmetric and unimodal. In other words, we peak in the center, and the more we go out from the center, the less likely our values are. Any student T distribution is going to be more spread out than a normal distribution. In other words, it gets shorter and squattier, but also wider. And the last quality is if we increase the number of degrees of freedom, in other words, the n size, then we're going to get something closer and closer to the normal distribution. In other words, if we make our n large enough, the student T distribution becomes very, very similar to the normal distribution. Okay. In other words, if we can ask or survey enough items, then we can more resemble the normal distribution that we're used to. All right. So let's look at a few examples. Sorry, I'm using a light here. I'm trying to do this at home. Sometimes it just wants to fall and not cooperate with me. Okay, so let's say that we have a simple random sample, but we only have a random sample of size 10. Notice that's pretty small. It's not a very large sample. But let's say the population is something that's normally distributed. But because we're only choosing a sample size of 10, it's going to be more difficult to make judgments about the whole population from only 10 values. Okay, but we're going to call the critical value just like we did Z with a subscript. We're going to do T with a subscript. So it's T and then sub area over 2. And the reason the area is being divided by 2, remember, is because there's 2 sides to it for a 95% confidence level or confidence interval. Okay, so this is going to look very, very close to what we did before. It's just we have to do a little bit different work, use a different table. So first we need to figure out what the degrees of freedom are. The degrees of freedom is whatever one less than our sample size is. Okay, so once you decide on the degrees of freedom, I'm going to move this away, so maybe pause this. Notice here on the table it lists degrees of freedom, okay? And then it mentions all the way down to, I think, 40, and then it starts counting like by 10s and sometimes 20s and then sometimes 100s. So notice we want 9 degrees of freedom, so we're here. And then you need to look at the area in the right tail. So we need to think about that for a minute. But what you can do down here is notice that down here at the bottom, I want a 95% confidence level, and I want it to be 9 degrees of freedom so I can come up here. So let's talk about what this area right here means. Notice the area in the right tail says 0.025. In other words, 2.5%. That should actually make sense, right? Because if you take 100 minus 95 and divide it by 2, you get 2.5%. So it's saying on either side of the middle, we have 2.5%. Okay, but you can also read from this bottom row here and notice that here's 95% and then just move your finger up to 9 degrees of freedom. So you'll need to practice doing that. Okay, so according to table A.3, the critical value is 2.262. Okay, so if you can't see where I got that, you need to pause it and pay attention to where I told you where to look on the chart. We look at where 9 degrees of freedom and 95% confidence level intersect, and they intersect at the value of 2.262. Okay. So the critical value would be this 2.262. So now that we know how to find, hopefully, a critical value, we're going to talk about how we're going to now construct a confidence interval. And you're going to do it much the same way as you did when you knew what the standard deviation is. All right, so how do you construct a confidence interval for mu when sigma is unknown? Okay, so number one is you compute the sample mean and the sample standard deviation if they aren't given. So we might have forgotten how to do that. We'll probably remind you of that in today's lesson. Okay, sometimes they'll be given, but sometimes you'll have to figure out what they are. Number 2 is you need to find the degrees of freedom. Remember, that's n minus 1. Because the degrees of freedom tells you where to look at on your chart. So find the degrees of freedom, which is n minus 1, and the critical value. And we call that T sub A over 2. Number 3 is you're going to compute the margin of error. So again, don't let the way that this formula looks throw you off. It's really just the same as we were doing before. The margin of error is going to be your critical value, which is this T thing, and then times the standard deviation you know over the square root of n. Notice this time I'm using S instead of sigma because I don't know sigma. Okay, sigma is my unknown, and that's why I have to have a new process for this. Okay, and then finally you're going to then find x plus or minus the margin of error. And once you do that, you'll have your interval. Okay, so let's look at an example and look at some of the wording that kind of indicates that we have a new scenario here. So let's say we had a sample of 1,972 adults. And these adults were asked how many years of education they had. Like not college, but total. The sample mean was 13.37 years. And the standard deviation of the sample is 3.13 years. So before I get to asking you a couple of questions about this, this is how this problem is different from what we did in 8.1. It's the sample of the standard deviation, it's the sample standard deviation, not the population standard deviation, okay? When that happens, we have to use our student T population, or student T distribution, instead, okay? All right, so I want you to construct a 98% confidence interval for the mean. Okay, so if we go through our steps, notice some of the stuff we were given, right? X bar is 13.37. S is 3.13. So I don't have to do step 1 because those things were given to me. So notice that my degrees of freedom is pretty large, right? It would be n minus 1, okay? But notice my chart only goes up to 200, okay? So when it goes up to something bigger than 200, then you just use this bottom row. Okay, notice what they call that. They call that Z. In other words, if you're greater than 200, we're going to assume that it's pretty close to the standard deviation, to the normal distribution. So let's go ahead and write that out. Since n is greater than 200, just use the bottom row. In other words, the Z row on table 1.3, A.3, Okay, so let's find the margin of error. So the margin of error is going to be what we find on the table. Okay, so again, if you need to pause it and get out your chart. So we're here, and we want to be 98% confident, which means we're at 2.326. So the margin of error, remember, is going to look like this. It's going to look like your critical value times your standard error. Okay, so it's going to be 2.326 and then times the standard deviation divided by the square root of n. Okay, so if you work that out on your calculator, it comes out to be 0.1639. Okay, remember this represents your error. I'm gonna go to the next page. I don't really have enough room here. So, the 98% confidence interval for the population mean. Notice how this answer looks very close to the ones we did in 8.1. It's just that our critical value is different. That's really the only change. Is going to look like 13.37 and then plus or minus this error of 0.1639. But usually I'll want you to write that as an interval, and so will Math Connect. So it looks like that's anywhere between 13.21 and 13.53. Okay, so notice this interval is pretty tight, right? It's pretty small, and that's because the standard deviation is pretty small, honestly. So in our sample of 1,972 adults, they had 13.37 years of education. And if we want to make judgments about the whole population, it's going to be somewhere in between these with a 98% confidence level. Okay, so let's use that to answer a question which I haven't really made you do yet. But let's say that in a certain year, the sample mean of the years of education for that year of adults was 13.26. And my question is, does this contradict the confidence interval we set up? Okay, so notice 13.26 is within the interval that we expected, so no, it doesn't contradict it. Okay, so I'm just going to say no, 13.26 is within the interval. It is within the interval that we expected, so it doesn't contradict it. Okay, by the way, it is possible for it to contradict it, right? Because we're only 98% confident, so there's a small chance that we could be outside of that window, but it shouldn't happen very often since it's, quote, 98% certain. Okay, so let's do a full-blown one. So this is going to be the last example, although we're going to do multiple parts, but it's going to take you some time. You're probably going to need to pause the video a couple of times. So let's say that we took a sample of 8 college students, and those college students were asked how many hours they sleep a night. So I think we've done a sleep example before. The difference here is that we're only asking 8 people. So it's a pretty small sample. And let's say these were their responses. So maybe we sent them a survey by email or something. So their answers were the following. We got a really sleepy boy here. 24 hours there. Maybe he had a really rough night the night before. Okay, but these 8 values are what we're going to use. All right, so first what I want you to use is that, or understand, is that we have a value that is outside what we expect. Remember, we used to call that an outlier. The 24 hours person we're hoping is a mistake anyway. Unless they're in some sort of alcohol-induced coma, right? Shouldn't be sleeping for 24 hours straight. So when that happens, we typically eliminate it. And then construct our confidence interval. In other words, if you know it's a mistake, don't include it in your results. Remember we talked about a Michael Jordan salary example where his salary threw everybody else's salary off. So they actually would have been better off to throw his salary out the window, and that's what we're going to do with this 24-hour sleeper. Okay. When we do that though, notice we're only going to have 7 values. So notice here I don't tell you what the mean is, but you can figure it out, right? So to find the mean, you would do the sum of all the values except the 24 and then divide it by 7. So if you want to, you can kind of pause the video and make sure that you get the answer I get here. But I get 51.5 for the sum, which works out to be 7.3571. The standard deviation's a little tougher, so it's been a bit, so I wanted to make sure we covered this. But remember, standard deviation squared is actually the variance. So remember, we're actually going to take the sum of all the x minus x bars squared and then over n minus 1 because it's a sample. So I'm going to start this out for you. But then I'm just going to tell you kind of what the answer is. So in other words, you take the first sleeper of 7.5 minus our average squared plus the next sleeper's amount of sleep minus the average squared. Okay. And then I'm just going to say plus dot, dot, dot. Okay. You're going to do that for everybody. You also could create a chart here if you really wanted to, but I think we can write it out kind of efficiently. So go all the way to the end. In other words, skip the 24 guy, right? But go all the way to the 7.5. And then we're going to divide this by 7 minus 1 because there's 7 values minus 1. So you might need to pause the video for a little bit, but you do need to make sure you can come up with your own standard deviation still and that you haven't lost that skill. Okay, so remember this is x squared or s squared, so then s would be the square root of that. Or it looks like about 0.7480. Okay, so remember these are the 2 values we need, right? We need this guy, the average, and we needed the sample standard deviation. Okay, we just had to go with our old school methods to find those things. Okay, so let's find the margin of error. So the margin of error is going to be, you need to look at the chart again. Okay, so the margin of error is going to be, you'll need to figure out what goes here. Okay, and what goes here would be, remember, 95% confidence for 6 degrees of freedom. Right, because our n is 7. Okay, so if you look at your chart and figure out where 95 and 6 degrees of freedom coincide with each other, it looks like 2.447. So that's what goes here. And then we're going to multiply that times the standard deviation we just got. And then over the square root of 7, since our n is 7. So if you work all of that out, let me punch that in. You get approximately 0.6918. Okay, so remember, this is the error. So our answer then is going to be X bar plus or minus this error. Or 6.67, between 6.67 and 8.05. In other words, judging by these few sleepers, these 7 sleepers, we can judge that probably the population of college students as a whole gets somewhere between 6.67 hours of sleep and 8.05 hours of sleep with a 95% confidence. Okay, and there's going to be one like this on your homework, so that's why I wanted to do one like this with you. So part B, let's say I want you to leave the outlier in this time. So let's say you weren't paying attention and you didn't notice the 24-hour guy. And then I want you to do the same thing, construct a 95% confidence level. Interval, I mean. And then I want you to tell me if the results are noticeably different. In other words, is including that one outlier really that big of a deal? Unfortunately, you're going to have to figure a lot of these things again, okay, because we have a new X bar. Notice this time you'll have to do the sum over 8. So you can pause it, make sure you get this, but 75.5 divided by 8 is actually exactly equal to 9.4375. Okay, certainly it changed the mean, right? It brought the mean up by like 2 whole hours. And then for S squared, remember we do the sum of all the differences between the values and the average squared. And then we divide that quantity by n minus 1. So again, I'm just going to do a couple of these. So you're going to do 7.5 minus the 9.4375 squared. And then plus the next one of 8.0 minus the 9.4375. And then I'm just going to say plus dot, dot, dot. Okay, but this time, remember, you got to include the 24-hour guy. It's kind of sexist that I'm saying it's a guy, but maybe a safe assumption, I don't know. So we end up getting S squared to be 35.1027. And so S is going to be approximately the square root of that. I say approximately because that's not an exact value to begin with. So it ends up being 5.9248. So these are the values I'm going to use this time. Okay, that's my mean and my standard deviation that I'll use. And so one more time, let's find the margin of error. So the margin of error is going to be different this time, right? So I'm going to need something here. And why is this going to be different? Well, because we're still doing 95% confidence. But this time it's for 7 degrees of freedom because n is 8. Okay, so again, you're going to look on your chart and see where 95 degrees of 95% confidence intersects with 7 degrees of freedom, and it looks like it's 2.365. But then we're still going to do it times the new standard deviation, which is quite a bit higher, 5.9248 over the square root of 8. So we end up getting an error that is a lot larger. The reason the error is so much larger is because the standard deviation was very spread out because of that 24-hour guy. And so just like before, now we're going to take x bar plus or minus this error. And so notice what we get is a much more spread out interval, anywhere from 4.48 hours of sleep a night to 14.39. That's a lot different than we got in part A, right? So to answer the second question, the results are noticeably different. So the moral of the story is, if you know you have an outlier, you actually shouldn't be including it in your calculations, or you're going to get values that are way off. If you compare this to what we got in A, that's a much bigger spread, and you know, it's probably unreasonable that on average people are sleeping anywhere close to 14 hours, right? Even adults don't usually get that much sleep, okay? I don't know, maybe in this pandemic you're getting that much sleep, but probably not on a regular basis, right? Okay. All right, so as usual, email me if you have any questions. This is actually the last section before we take test 3. So you really need to practice using your charts, knowing when to use 8.2 and when to use 8.3. And the answer to that question is you use 8.2 when you know it's a normal distribution or a bell curve. You use 8.3 when either A, you need a certain critical value for confidence intervals, or when you have any sort of degrees of freedom situation.